So the first thing we do before we start talking about the chain rule is we're going to just look at a very, very simple function that we know how to take the derivative of. Right? Y equals 6x minus 10. You know how to take the derivative of y equals 6x minus 10, right? Yeah. So this is the part where you unmute yourself and say, yes, I can take that derivative.
I can take that derivative.
There you go. That's exactly the way we do this. That's good work. All right. So what we're going to do is we're going to rewrite this function, though, before we take its derivative as y equals 2u. So if this function is y equals 2u, what would u have to be to make it still equal 6x minus 10?
3x minus 5.
Right, u would have to be 3x minus 5, right? 2 times 3x minus 5 gives us 6x minus 10. Would you all agree with that?
Yes.
All right, perfect. Okay, now we're going to find 3 different derivatives here. The first one is the one you already told me that you knew how to take the derivative of. So I want to find dy dx. So that means take y and take its derivative when it's in terms of x. So the derivative of y in terms of x should be what?
6.
6, right? The derivative of 6x minus 10 is 6. All right, now, so that came from here. Now I want you to take the derivative of y, but take the derivative of y when it's in terms of u. So what would you get if you took the derivative of
2?
Yeah, that's just 2, right? And then lastly, I want you to take the derivative of u when it's in terms of x. What would you get?
3.
3. Ah, man, it's like you guys can take derivatives. This is good news. All right. Now, for the amazing thing, there is a very, very special relationship between these 3 numbers. 6 is equal to 2 times 3. Isn't that a very special relationship? Yeah. And you have just done the chain rule. You have found that the derivative of a function with respect to x is equal to the derivative of that function in terms of u times the derivative of u in terms of x. This right here is the chain rule. Okay? The chain rule helps you to take the derivative of a composite of 2 functions. Now, obviously, we didn't need to write y equals 6x minus 10 as a composite of 2 functions, right? But if we did, we would find that its original derivative is just the product of the other 2 pieces that we wrote as the composite multiplied together. Okay? So dy dx is equal to dy du times du dx. Sometimes we write this in a couple of other different ways. Because sometimes we write, instead of writing a composite function like this, sometimes we write it as like f of g of x, right? You've seen that before?
Yeah.
Okay. So the way that we, and I'll show you on the next page, the way that we would write the chain rule for a composite that we might write like this is equal to f prime, the derivative of f, with g of x plugged in for it, times the derivative of g. And so that's effectively what we've got here. We've got the derivative of y. Y is the outer function, right? F is the outer function, y is the outer function. It's the derivative of y evaluated at the inner function u. And this is the derivative of f evaluated at the inner function of g. And then it's times the inner function g, or times the inner function u. So these are the same things. The derivative of a composite of 2 functions is this or this. And sometimes they write it like this, but I will never probably write it like that. This is the chain rule. Okay? It works for any composite function that you can write. So you remember, I hope, I gave you guys one like this, something probably like 2x plus 5 to the 2nd power or something like that. And people probably said, oh, let's use the power rule, right? You remember when somebody might have said, like, let's use the power rule for that?
Yeah.
Yeah, and you might have been like, oh, it's 2 times 2x plus 5 to the first power. Well, no, because this is a composite of 2 functions. This is y equals u squared with u equal to 2x plus 5. And so the derivative should be the derivative of this times the derivative of this. Okay. So what's the derivative of u squared with respect to u?
2.
2u. And what's the derivative of u with respect to x?
2.
2. So here, if we multiply these together, what do we get? We get that dy dx is equal to 4u, or 4 times 2x plus 5, which is not the 2 times 2x plus 5 that we thought it should have been, right? It's the 2 times 2x plus 5. It's that power rule that you might have tried to do times the derivative of 2x plus 5. And that's how you do the chain rule. Easy enough?
Yes.
All right. Hopefully that made sense. We're going to go through and do a bunch more of them. But does anybody have any questions on this? What the idea behind it is, or the process that we're going to use is? All right. So this one's very similar to the one we just did, right? We're going to use the chain rule to find the derivative, and then we're going to distribute it out and use the power rule just to make sure that we did it correctly. Sound good?
Sounds awesome.
There we go. I was gonna say, this is the part where you say yes. That was even better. It sounds awesome. Yeah. All right. So let's try to write this as a composite of 2 functions. What does y equal if we substitute out some piece of it? What can we substitute out to make this into some simple function here?
U squared.
Yeah, u squared, right? With u equal to?
3x squared plus 1.
Perfect. So we got y equals u squared with u equal to 3x squared plus 1. What is dy dx? It should be the derivative of this, which is, what's the derivative of u squared?
2u.
2u times the derivative of u, which is
6x.
6x. So it should be 12x times u, right? And u is 3x squared plus 1. So it should be 12x times 3x squared plus 1. That's the derivative of 3x squared plus 1 squared. Now we could show that this is true. If we distributed this out first, what would we get? We would get 9x to the 4th plus 6x squared plus 1, right? If you distributed this out first.
Yeah.
And if you took the derivative, differentiate this, we'd get 36x cubed plus 12x. And well, sure looks like we could take a 12x out of that, right? And get 3x squared plus 1. Which looks exactly the same as what we got the other way with the chain rule. Nice thing about the chain rule too is that sometimes it'll give you a nice factored form of it. Isn't that exciting?
Super exciting.
Yeah, all right. Any questions on that? Because they're just going to get worse. All right, let's do another one, another simple one. and then see if we can verify it using a trig identity. So what piece of this makes it a composite function? It's the fact that it's got a
Two X.
Instead of X.
it's got the 2x, right? That 2x is making it a composite function, because if it was just sine x, well, if it was just sine x, the derivative would just be cosine x. But as soon as I throw an extra term in there, it's no longer just sine x, it's sine of some other function, sine of u. So we'll call this y equals sine of u, with u equal to 2x. And what's the derivative of sine of u with respect to u? What's the derivative of sine?
Cosine.
So cosine u. What's the derivative of u with respect to x?
2.
So we should get 2, we'll say dy dx is 2 cosine u, or 2 cosine 2x. We just replaced the u with what we originally said u was. Good or no?
Good.
All right. Now, we should have been able to already find this derivative. What is the double angle identity for sine that I know you have memorized, because it was on that trig sheet that I asked you to have everything memorized on?
Sine time 2 times sine times cosine x.
2 sine x cosine x. Yep. And so this is just two functions being multiplied together. This is just the product rule that we could use, right? If I wanted to, we'd end up with 2 sine x times the derivative of cosine, which is negative sine, plus the derivative of 2 sine, which is 2 cosine, times cosine. And if we write that a little simpler, it'd be 2 cosine squared x minus 2 sine squared x, which becomes 2 times cosine squared x minus sine squared x. And I know that you know, based on the formula sheet that I told you to memorize, what is cosine squared x minus sine squared x? Like you guys didn't memorize it. Cosine squared minus sine squared is cosine 2x. And look, they're the same. Isn't that great?
Oh yeah, how exactly did you get derivative of y equals 2 sine times minus sine x plus 2 cosine x again?
Right here, this term.
Yeah.
That's the product rule.
Yeah, all right.
Any other questions there? Everybody okay with this? All right, let's do another one. Here is a position function given to us. X of t is cosine of t squared plus 1. We want to find the velocity function. So the velocity function ought to be the derivative of the position function, right?
Yep.
Okay. So, well, we could write this as the position is equal to cosine of u, with u equal to t squared plus 1. So we'll call this how about x of t, or x. X is equal to cosine u. with u equal to t squared plus 1. So how do I find the derivative of this? I should take the derivative of x with respect to u, which is what?
Negative sine u.
Negative sine u. And I should take the derivative of u with respect to t, which ought to be
2t.
2t. And so our derivative, v of t, ought to be those two things multiplied together. Negative 2t sine of u, and u is t squared plus 1. So we'll hopefully note that for these simple chain rule ones, right, we have the outer function is, in this case, the outer function is cosine, and the inner function is t squared plus 1. And so it's the derivative of the outer function, negative sine, evaluated at the inner function, so negative sine of t squared plus 1, times the derivative of t squared plus 1, which is the 2t. So sometimes we refer to this as the derivative. I'll write it all the way out. We say the derivative of the outer function evaluated at the inner function, and then times the derivative of the inner function. So if you don't necessarily like writing out all of this, that's fine, as long as you can successfully do this in your head, that's fine. And I would like you to eventually get to the point where you just look at cosine of t squared plus 1 and tell me, oh, yeah, the derivative of that is negative 2t sine t squared plus 1, and just be able to do that in your head, hopefully. Not yet, probably, but soon enough. Any questions? Everybody okay? Let's do another one. We want to differentiate. I'm going to take the derivative of sine of x squared plus x. So this is sine of
U.
u with u equal to x squared plus x. The derivative of the sine of u is cosine u, and the derivative of x squared plus x is 2x plus 1, so just multiply them together. 2x plus 1 times the cosine of u. Any questions or issues with that? All right, let's do another one. We've got f of x equals the square root of x squared plus 1. What's the outer function?
The square root of u.
Square root of u. What's the inner function?
U equals x squared plus 1.
What's the derivative of the outer function? It's 1 over 2 root u, right?
Yeah.
The derivative of the inner function, 2x.
Yeah.
So multiply those together, we end up with 2x over 2 root u.
X over.
Yeah, cancel off the 2's and you got x over root x squared plus. Any questions or issues with that? Everybody feel okay about that or no? Anytime it can be written as a composition of two functions, you've got to use the chain rule. So you can't just go in and say, oh, this is square root, so it's 1 over 2 root x squared plus 1. No, you have to multiply that by the derivative of the x squared plus 1.
For the last one, is it cool if we leave the square root in the denominator?
Oh yeah, I know all your other math teachers ever have told you can't have a square root in the denominator. That's just some arbitrary garbage that somebody said sometime. It's not. It doesn't matter. Square roots are fine in the denominator. In fact, please leave them in the denominator. Please don't get rid of them. I'll break you of that bad habit of rationalizing denominators right now. Just makes life more complicated. It's not your fault that you have that bad habit. It's all of your previous math teachers. But unless one of your previous math teachers was somehow me, and then it wasn't my fault. All right. What about this one? What can I write this as?
1 over u
Just 1 over u.
All right, it could be 1 over u cubed, which would then require us to use the reciprocal rule, right? Or how else could we write 1 over u cubed so that we didn't have to use the reciprocal rule?
u to the power of -3.
Yeah, u to the power of -3. So we've got y equals u to the -3 with u equal to 4x squared plus 6x minus 7. And if we can write it in this form, we can just use the power rule for that, which is what?
-3 to the power of -4.
-3u to the negative.
Yeah.
And then du dx ought to just be 8x plus 6, right? So multiply them together. Let's see, we have a -3, right? So -3, and then an 8x plus 6, and then over u to the 4th.
Yeah.
Anybody have an issue with that?
Oh wait, can you jog my memory on the reciprocal rule again?
The reciprocal rule, it just says if I have 1 over a function, the derivative is -g prime over g squared.
Yeah, all right.
So you could use that if you wanted to, but I think it's easier to just write it as a negative exponent and use the power rule.
Where did that that -4 go on you?
Where did it go?
Yeah, because I mean, you got the -3u to the 4, or the -4. Where'd that go?
Right, the -3u to the -4. So there's the -3 part, and then this is my u to the -4.
I see. Okay.
Drop it to the denominator. You could have written it up in the numerator as 4x squared plus 6x minus 7 to the -4 if you wanted. But yeah, normally we'll write it as a positive exponent, especially if it's like a big term inside of it. Anybody else have any questions on this one, or any conceptual questions on the chain rule? No? All right, let's do another one. Cube root of 5x squared minus x plus 4. This is u to the
1/3 power.
u to the 1/3 with u equal to all that garbage inside the cube root. What's the derivative of u to the 1/3?
1/3 u to the -2/3.
Perfect. And the derivative of 5x squared minus x plus 4 ought to just be 10x minus 1. So we just need to multiply those two things together, right? That's going to give us a 10x minus 1 in the numerator. It's going to give us a 3 in the denominator, and then we'll take that u to the -2/3 and drop it to the denominator as a u to the +2/3. Good or no?
Good.
All right, I think that's probably, yeah, I guess we could do this. Nah, we'll wait there. We'll stop right there. That'll be good for today. I don't want to, the next one's going to take a little bit too long to get all simplified down. That's the basics of the chain rule. Any questions on that?